Our next set of video lectures concentrate on optimization problems. Now, optimization problems are probably one of the biggest applications to calculus, at least differential calculus. And before we look at specific examples, we're going to first take a look at kind of the overview. What is an optimization problem, and what are some general strategies that one can use to go about solving and understanding optimization problems. So first of all, let's define an optimization problem. So what exactly do we mean by this? So an optimization problem occurs when one wishes to determine the maximum or minimum value of a certain quantity Q that depends on one or more physical variables. So by physical, I just mean that they're, real-world variables. Distance, the number of tickets you sell for a theater show, radius, etc., pressure, these sorts of things. So the variables all have a practical interpretation. Now, one of the things that is a little bit unique about this topic that we haven't seen before is that some of these optimization problems will involve more than one actual variable. So you're going to be optimizing something that is a function of two or more variables. And whenever that comes about, we need something to reduce the dimensionality, because so far we've only developed tools for one-dimensional calculus. So without going into three-dimensional calculus, we need something extra that will help narrow down our search. And that something extra is called a constraint. So a constraint is a relationship that must hold between two or more of the physical variables. So for example, you might say optimize the volume of a can. So suppose you're manufacturing cylindrical cans. Now the volume of a cylinder depends on both the radius and the height of the cylinder. So the volume is going to depend on two variables, radius and height. So there's something extra. So you might say you're only considering cans whose height is twice the radius. So there might be a certain proportion. Or you might say find the maximum volume of a cylindrical can given a fixed surface area. So we want to use this much material to construct the can. What size can should we make that will hold as much as possible given this limitation on how much material we can use to construct it? So using that constraint, which in the previous example was how much material you have at your disposal, you can basically eliminate one of the variables in terms of the others. So that's the main idea behind optimization problems. You have some quantity Q that varies as a function of other quantities, or maybe just one other quantity, and then you want to find the maximum or minimum values of that function Q on a given domain. So of course you always want to check your boundary points. So this is where the 4.1 material comes into play, local and global minima and maxima. You always look for critical points inside your domain, and then you also check your boundary points. So we'll be using all those tools that we've already established when we go about solving these problems, except these are a little bit more challenging in that it requires additional problem-solving skills. So in this module, we're not really learning any new mathematics. So the tools that we need to solve these problems we already know. However, we haven't refined all of the skills to go about solving the problem. So when we're talking about problem-solving skills, it really It's not necessarily a direct approach where you do this, 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 and this, and there's the solution like you've seen in pre-calculus mathematics, algebra, geometry. It's really about getting to know the problem, understanding the problem, and thinking about it. And sometimes that can take hours, or you might come back to it over a period of days. But that's okay, because these are not problems that you're going to solve right away. They're problems that are going to take time. When I was taking thermodynamics as an undergraduate, there was a problem in the book that said, here's the pressure, volume, temperature of a gas in a box. And we're going to add so much heat, raising the temperature to this new temperature. What's the new pressure? And so obviously you're going to use the ideal gas law. Pressure times volume is equal to the gas constant times temperature, or pressure times specific volume. But there's a relationship that links pressure, volume, and temperature. The only problem was I didn't have two of the unknowns. So I only had one equation and two unknowns. And I spent 3 hours trying to figure out what the heck to do with this problem. And finally it dawned on me, oh, it's a box of gas. It's in a fixed container that doesn't move. So the volume before is equal to the volume later on. Really simple answer, right? But I spent 3 hours thinking about it before I figured that out. That was the hidden constraint. The initial volume is equal to the final volume because it's in a fixed box of gas. So sometimes there are little subtle things that you have to really pick up on, and it takes thinking about the problem, thinking about it different ways, taking different approaches. So the following guidelines are things that can help you start thinking about problems. And you might not necessarily use all of these on every problem, or you might use some of them on some problems and other ones on the others, but they're just a general set of problem-solving guidelines. So we'll call this strategies, and specifically for optimization problems. So the first strategy, the first step, I cannot emphasize this enough, read the problem. You might say, well, that's obvious, you have to read the problem. It's not obvious, because a lot of people get problems wrong because they don't read the problem. And you might glance at the problem, you might do a quick read, and oftentimes you might think it's saying one thing, but it might subtly be saying something else. When I say read the problem, I mean very carefully read the problem. Read the problem twice, in fact. So make sure to really absorb what the problem's asking. What information are you given? Is this a constant or is that a variable? So you have to kind of read into the problem a little bit. Does this mean that or that? And in addition to reading the problem, I also say write the problem. So they say write the problem. Or let's say write down the information. Write down the info. So make your own notation, write down everything that the problem gives you. If it says, here's a function, and at this altitude you have this pressure, say P of 500 is equal to this pressure. And try to write it down in mathematical notation. Anyway, but take the actual information pieces, which are data points. There are statements about if this variable is equal to that, then this variable is going to equal that, or this variable will be changing at this rate. Anything like that. Get all the actual mathematical information you can out of the problem and write it down separately. Then identify, so that right now this is very general problem solving. Identify what you're trying to find out. So in your mind you put a picture of these are the things that I'm given, and this is what I'm trying to find out. And then you try to construct a logical bridge. Okay, well, how do I get to these pieces to this piece over here? And it might be a bridge with several links to it. You might say, well, I have this information, and I can use some relationship or some principle to get this new piece of information. And from that, I can solve this new piece of information, and that will take me to what I'm trying to figure out. So sometimes you can't always get to where you're going in a single step. But the important thing is not to become frustrated or anxious about this process. And to do that, take this and approach problems and become more proficient at it, you have to give yourself time. And it has to be leisurely. Because when you're stressed out, your critical thinking, your frontal lobe isn't going to be functioning the same as if you give yourself more leisurely time to actually approach a problem, think about it, maybe have a coffee somewhere at a little cafe, sit back, relax, follow wherever your mind takes you. Make it fun. How do I solve this problem? Somewhere all the information I need to know is there, but how do I put it together? So spend time and make it enjoyable. So now getting back onto strategies specifically for optimization problems. Of course, this is a bit of a general strategy. Draw a picture. This is not something that you will always do. But if it's a physical situation, like you're pulling a boat towards a boat dock, okay, there's some sort of spatial relationship between the objects. We'll draw a sketch of it. If there's a person running around a baseball diamond, draw a baseball diamond and say, okay, here's this person, he's running this way, and this person's running that way. If there's two trains or two airplanes, draw a picture of the physical, spatial relationship of the different things in the picture. If you're dropping gravel on a conical pile, draw a picture of a cone so you can imagine that pile growing larger. Sometimes pictures can be abstract, and a lot of that happens with control volume analysis and engineering. So, for example, conservation laws, rate in, or the rate of change of a system is equal to the rate in minus the rate out. So the rate at which mass in a closed volume is changing is equal to the rate at which mass is coming into the volume minus the rate at which mass is leaving the volume. That's conservation of mass in a differential form. So there you might just say, okay, I have a box. Here, just draw a box and say arrows. Okay, I have water flowing into this tank this direction. I have water coming in that way. These are the rates. I'll label the arrows coming in, 20 kilograms per second or whatever the rate is. Okay, then I have stuff coming out here, so there's an exit rate. So sometimes even with an abstract sort of situation, you can draw an abstract diagram indicating flow rates in and out of some sort of closed system. So draw a picture can even be something like that. We might not necessarily do anything like that yet. Maybe you will, I'm not sure. 3, assign variables. And here you have to be careful because sometimes the problem tells you what the variable names are. It says, let Q be some quantity, and then it depends on the height X and the other height Y, or one length X and the other length Y. If the problem tells you what variables to use, stick with the problem's variables. If it doesn't, if the problem's silent, if it says, find the maximum volume of the cylinder, okay, assign your variables. Say V is the volume of my cylinder. R is the radius of the circular base of the cylinder. H is the height. And actually write down the variables that you're using. Because I see this a lot in Calc 1 and Calc 2 where students will start a problem. They have some variables in their mind, especially when problems get complicated. In particular, I'm thinking about some of the volume and work problems from Calculus 2 where you might say, okay, X is the distance between the water level and the top of a swimming pool, or some depth beneath the surface. And you start setting up equations, and then suddenly, this is a long problem that could take several pages to solve, and suddenly you're thinking, oh, X is the height from the bottom of the swimming pool, and then you're formulating equations later on, we're using a different meaning for the variable X. Well, you have to use the same meaning and be consistent with whatever variables. So it's a very good habit to get into to always write down your variables. So if you're defining R as the radius, actually write on your paper, R is equal to the radius of the base. H is the height, say H is equal to the height. Even if it's a simpler problem from these optimization problems, or it's something that you're not going to lead to confusion, get into the habit of that. That will also reinforce the meaning of the variables in your mind. So assign variables. If they're given to you, use the ones that are given, variable names. Identify anything that might be a variable and give it a variable name so that then you can manipulate and write down equations. Identify your constraints. Identify constraints. So if this comes into play when there's more than one variable. if there's more than one variable and you're trying to optimize the volume, and the volume depends on both radius and height, well, somehow there has to be some constraint, which is basically a way to link the radius and the height. It could be subtle. Maybe your productivity is a function of how many hours you spend sleeping and how many hours you spend studying. This was actually on a Calculus 3 midterm when I was taking Calculus 3. We had to use a different technique, but the question was, here's an actual function of x and y. X represents the number of hours a day you sleep, and y represents the number of days you're studying. So the student in question spends all their time sleeping or studying. Maximize the productivity. Well, how do you do that? There's two variables, and how do I... And it was on an actual exam. It's, how do you do this? And eventually, when I kind of calmed down and stopped stressing about the fact that I didn't know how to solve it, I thought, well, wait a second. Well, there has to be something, right? There has to be something that's obvious here, or not so obvious. Two variables, you can't do it if you have one function and two variables. You need some way to constrain them. There's 24 hours in a day. X plus y equals 24. Now I can solve the problem. But it didn't explicitly say, that, but it says, hey, they spend all their time sleeping and studying. X, how many hours per day they sleep. Y is the number of hours per day they study. There's a constraint. It's a hidden constraint. It's very subtle. X plus y equals 24. They didn't tell me that, but it's like, oh, okay, there's 24 hours in a day, so the total number of hours has to add up to 24. So make sure to be on the lookout for subtle constraints like that. Sometimes they are subtle. Now, with these optimization problems, next step is to reduce the variables. And in general, let me say one more thing on constraints. If you have two unknown or two independent variables, you'll have one constraint, because then you can write one variable in terms of the other. We probably won't see any of this, but in case you ever do, if you have three independent variables, you'll need two constraints, because you want to get rid of each constraint is one equation, and one equation allows you to eliminate one variable. So think of each constraint you can knock out of one of the variables, and you need to get it down to a single variable that you can then perform calculus with. So reduce the variables. So if you have two variables and one constraint, eliminate one of the variables. And to do that, you solve for one of the variables in terms of the other variable. So it says, okay, if the height of the cylinder is twice the radius, h equals 2r. Okay, so h is equal to 2r. I explicitly have the height as a function of the radius. Now let's replace height in the volume equation with 2r. And now volume only depends on r. And basically, whatever value of r you take on the domain, the height is chosen to satisfy the constraint automatically. 6, identify the domain. So you don't want to just take the derivative set it equal to 0, because your critical point might lie outside of the domain. Most problems, you're okay. You're just looking for the critical point, and that's the answer. But sometimes there can be problems set up where, okay, you have 200 seats in this theater, and we're going to maximize this relative to the number of seats we sell. Maybe there's a critical point at 250. Maybe it's a maximum profit at 250. And say, okay, well, the answer is 250. Oh, you don't have 250 seats in your theater. You can't do that. It's outside of the domain. So the domain won't be necessarily explicitly given to you like it was in the previous sections. Optimize this function on the domain 0 to 4. No, it's going to, there's going to be physical constraints. Oh, well, x is a length, so lengths have to be greater than or equal to 0. So x is greater than or equal to 0. And then there's only so much room in this space, so it's going to have to be less than this maximum amount of room that I have in the given problem. So these are kind of the general strategies, things to think about, and we'll see how these are all applied as we go through a number of examples. But those are the basic problem-solving strategies for these optimization problems.